So we're looking at roots of unity here. We looked at complex roots of complex numbers, and the roots of unity takes that one little step further, where we can use a new identity or value, which is called omega, to help us represent the smallest possible argument and all different types of arguments in terms of complex roots. Now the omega, in its terms of representing the smallest possible argument, is the argument where we have some kind of 2 pi over n without the k value. So if we looked at the calculations of what we did in our last lesson, which was z cubed is equal to 1, we know that your roots of unity will be written out as 1 plus omega squared plus omega cubed plus omega n minus 1, which will all equal 0. If it's a true root, then they all should add together to give you a 0. And when we're looking at roots of unity, if you look at the variable we're looking at 1, it kind of looks like we're just dealing with the variables up to a 1 value. So if we looked at this example and take our information that we got from our last video, that we know that we're going to be using k values of 0, 1, and 2. And when we plug them into the variables of 0 plus k 2 pi, we ended up getting something that kind of looked like this. Cis plus k 2 pi on 3, and that was our, what we would consider our smallest possible argument. So if we look at these type of calculations in terms of where k equals 0, when k was equal to 0 and we had cis 0, we ended up with 1. When we had cis, when k was equal to 1, we had cis 2 pi on 3. And when k was equal to 2, we had cis, and I'm going to go and break the rule here, on 3, or negative 2 pi on 3. But we're going to leave it like this here so we can see how those calculations come across. When we look at these variables, when k equals 0, in terms of the small roots of unity, this here would represent 1. When k was equal to 1, what we did here is we had our smallest possible argument. So over here, our smallest possible argument then will be represented by omega. And when k was equal to 2, this here was rewritten as, can be written as omega squared. Now I do want to make the point here. Squared does not mean that I'm squaring these across, okay? Squared means I'm multiplying these here by the k value, which was 2. So for instance, if I had, this was to a power of 4, my next one here would be omega to the power of 3. It's always going to be followed that same rule. Your k value, whatever equals, represents the power of each of those omegas with the exception of the first one. If we remember the work we did from the last lesson as well, we knew that the coordinates for this was 1. The coordinates for this one was negative half plus root 3 on 2. And the coordinates for this one, negative half and root 3 on 2. So when we're doing our calculations, all these roots here, all these Cartesian points, when I add them together, I should get 0, which tells me I've found all my roots. So we did that in this case up here. Let's put all the information that we have. We have 1 plus the variables for omega were negative half plus root 3 on 2. The variables for omega squared, negative half, and that was minus as well, minus root 3 on 2. Now if I add all these together, remembering that they should equal 0, 1 omega and omega squared. That should all equal 0. If I found out all the roots, then that should equal 0. Well, let's have a look. 1 take away a half, or let's look at these two. These two will cancel out. Then I've got a negative half, and a negative half gives me 1. So therefore 1 minus 1 does indeed give me 0. So we have found out all the roots of our roots of unity of our complex number. Another way that you can actually sketch this is by using what we call a vector form. So we know that this here should give us a triangle. So if we drew our vector forms in triangle form, it should follow the same premise as I had before. So I start off with 1, then I've got omega, and then I've got omega squared. Oh, really exaggerated that one, didn't I? Omega squared. Where if we had another point where we had to the power of 4, then you would have 1, and if we did this to a power of 4 now, you would have 1, the smallest possible argument, squared, and cubed. Making sure that you come back to your original point so you can finally get to where you started from. Okay, so when it comes to roots of unity, we're now carrying on from what we did with roots of complex numbers, but instead of now calculating your coordinates or your positions to polar form, we now say, well, k0 is your initial point, so that gives us 1. You're always going to have 1. The smallest possible argument when k equals 1 is now represented by omega. When k equals 2, omega squared, and so on. All the way up until we get plus omega n minus 1, which lines up with this calculation here. And that equals, should all add up to 0. So if I had to the 4th, then I'd have omega to the power of 3. That's our connection between the roots of unity and the roots of complex numbers. So remembering now we have these kind of variations, remembering this here is how we represent the smallest possible argument, which is omega, and they should, if we do a vector diagram, should come back to its original point and match up with the regular polygon that we looked at when we did roots of complex numbers. Good luck, and I'll see you in the next one.